All right, folks, so we introduced this or reintroduced this concept of a diene in our last video, right? And I told you to come back. We're going to have a chat. We're going to dig up an old topic called diene, and we're going to review it. We're going to look at it through a whole different perspective. Okay, so diene, di means two, ene means double bond. So we have two double bonds at least in a molecule. That is a diene. A triene would be 3, tetraene would be 4, and so forth. But there's two different types of dienes that we might see in organic chemistry. The first type of diene is something called a conjugated diene. And the second type of diene is called an isolated diene. All right, so what are the differences here? Well, an isolated diene means that this thing is separated by more than one double bond. And conjugated dienes, well, this means the dienes, the carbon double bond carbons, are separated by only one single bond. And I just made a mistake. I was thinking about doubles, and I said a double, but I meant single. So conjugated dienes are basically this. It is a carbon double bonded to a carbon with a single bond, and that one has another double bond. Double, single, double, double, single, double, double, single, double, double, single, double, double, single, double. That's a conjugated diene. Those are very important to us, and you'll see why in just a little bit. The isolated diene is similar, but they're a little bit further apart. They're separated by more than one single bond. So carbon, double bond, carbon, single, and then maybe another single, and then the double happens. This is not a double, single, double, double, single, double, double, single, double. This is a double, single, single, then double. That is not a conjugated diene. This is just the regular old diene that we have come to know. So two different versions of a diene setup. They're either going to be conjugated, like the one over to the left, or they're going to be isolated, like the one on the right. The one to the left, I'm putting stars around, because, folks, that's the tricky one. That's the one that we're going to have to pay special attention to when it concerns reactions. Because reactions is going to be coming back with a brand new one at the very end. We're also talking about delocalized networks, and we're also talking about the electron movement. So if we're getting ready to talk about reactions, we also need to talk about carbocation stability again. And there was something that we called the allylic carbocation. Do you remember what the allylic group was? It was a carbon, double bond, carbon, single bond, and attached. That was the allylic carbocation. So this would be the allylic carbocation. Folks, look at that structure. What do you see? I hope you're going to tell me delocalization, because delocalization is going to happen. Here we have a double bond moving toward a positive charge. That was rule number 1. Delocalization can happen. And what do we say about allylic carbocations and delocalization? If delocalization can happen, it improves the stability of the molecule. And now we can kind of go back and talk about the allyl group and where that carbocation fit into the chain. Why was it more stable than some of the others? Well, we now know why. Delocalization plays a role in that. The other carbocation, maybe a new one that we really haven't talked about yet, is something called the Benzylic Carbocation. The benzylic is my benzene ring. My benzene ring is this with a circle. This benzylic cation, folks, has its stability because of delocalization. That is why it is more stable than some of the other ones that are out there. There's more resonance contributors. There's more resonance forms. And the more resonance forms, the more stable the molecule is, the happier that it's going to be. So the allylic carbocation, different resonance forms. The benzylic carbocation, really didn't fully draw that one, did I? It's the benzene ring with the carbon that has a positive charge on it. That has many, many different resonance forms. And these now are located in the carbocation setup. The tertiary, the secondary, the primary, we've kind of already positioned them where they needed to be back in the day. This was just bringing that back up again and talking about maybe one more time and confirming and reaffirming why they are in the position that they are. So if you need to know that carbocation ranking because you can't really find your notes and you don't know where it is, well, here we go. Here's a diagram of it. The only new one probably is the benzyl, because we really haven't talked about benzene up until this point. But all the other ones we have kind of sandwiched in where they needed to go. So here's the tertiary carbocation, which is still the most stable. And here on the tail end is the primary carbocation, which is typically the least stable. And this is the most common least stable one that we see. Yeah, there's methyl cations and there's vinyl cations. We rarely see these, though, in reactions, and the only time that we would see something like this is if they were really super simple molecules. But tertiary comes first, benzyl is next because of the resonance forms, then allyl. Notice they wrote them as equivalent in a way, and then a secondary carbocation, which is also kind of equivalent to the allyl, which is very similar to the benzyl. So they group kind of all three of those together. All right, let me go back. They group all three of those together in one lump. And then the primary comes at the tail end. Now, there are different types of allylic and benzylic cations. All right. So what you see on the screen right now are just different versions. As you can imagine, this particular carbon, that is carbon, double bond carbon, delocalization can happen right in here, but this carbon could be attached to two others. And this is what we call a tertiary allylic. Here, we see the same thing, but that carbon is only attached to one other carbon. And this is our secondary allylic, because it's attached to two carbons. And then finally here at the very end, this is our allyl cation, and it's a primary allylic. And it's primary because this carbon is attached to only hydrogens. It's only attached to one other carbon, and that is it. So within the allyl family, we still have tertiary, secondary, primary. So if we do have allylic, and we're trying to compare one allylic to another allylic, then we can look at the groups that are attached onto that carbocation in order to determine the order, the priority, and the ranking. The same thing's going to happen down below with benzylic. Benzylic is in its spot. Overall, we know where that is now. It's kind of right behind the tertiary, grouped with the secondaries. But within the benzylic family, folks, we still have a tertiary, secondary, primary. Well, it's just the same as before. Here's my carbocation. 1, 2, 3. It's attached to three other carbons. So that is a tertiary benzylic. And then this carbocation is a secondary benzylic. It's only attached to two others. Hydrogen we don't count. And then finally here is our primary benzylic. So this is my carbocation. that's only attached to one other carbon, and that's the carbon to the left. The other two are hydrogens. We don't count them. So there's my primary version. Again, all of this is made possible by delocalization. And the reason is because electrons can move toward a positive charge. And this can start to rearrange the molecule. Delocalization begins to happen, and delocalization begins to stabilize the molecules when they form. On the benzylic side of the house, well, look at this. Double bond can move toward a double bond. Double bond can move toward a double bond. Double bond can move toward a carbocation. There you go. So this is actually delocalizing the whole entire ring. The whole thing. The whole shebang is getting delocalized. So delocalization plays a role in stability. Delocalization plays a role in reactions, and we're going to soon find that out. And delocalization really plays a role in carbocation stability, because now we know these are two important ones that we have to watch out for. Now, let's see what we're building up to. So let's clear the screen. And let's go back and revisit maybe an old reaction. This time, though, we're going to add on a benzene ring. CH, double bond, CH, CH3. And we're going to add on HBr. We're only going to use the rules that we've talked about before in the alkene lecture. All right? Here's an alkene. Alkene reacts with HBr. Well, I look at the double bond. The double bond breaks. I mean, you remember those lectures, right? And H goes on one side and Br goes on the other. All right, not a big deal. So what I'll do is I'll redraw what they want me to start with. And I'll just replicate it. Again, I think it's the easiest. And then I break the double bond. There we go. Two sides of attachment open up here and here. H goes on one side, Br goes on to the other. All right, well, where does the H go? H goes and plays with other H's. All right, so here we see a carbon with a hydrogen, and to the right we see a carbon with a hydrogen. They both have hydrogens on them. They're both just one hydrogen on them. So does hydrogen really have a preference? And the answer is, yeah, it does. It does. And the reason is because we prefer the most stable carbocation to form. That's why H plays with other H's. That's why Makovnikov's rule goes forward every single time. So in this setup, what we have, if a carbocation forms here, this is a benzylic carbocation. If the carbocation forms here, folks, this is just really a run-of-the-mill secondary. And now I'm comparing a secondary to a benzylic. If I look at that particular type of benzylic, then it's a secondary benzylic. I've got a carbon to the left and a carbon to the right. That bond that points up, that goes to nothing right now. Remember, I broke the double bond and I added two dashes to represent these are the locations where the incoming groups are going to go. So out of the two, notice in that ranking, they said, they're about equivalent. You know, benzylic and allylic and secondary, they're about the same. But notice what they did. They put benzylic first. The reason is because delocalization plays a slight role in this decision. The delocalization of the benzylic carbocation improves the stability slightly over a secondary. Even though overall, when we compare them, we kind of look at them tertiary as way more stable than the grouping of this benzylic and allylic and secondary, which is way more stable than the primary. But in that grouping of three, benzylic has a slight improved stability over the secondary because of the delocalization. So when I go and add on my H, I'm going to add the H on to the carbon that is the least stable. That was what Markovnikov rule basically said. So hydrogen's going to go here. And this will allow me to form a carbocation at that position. That is a benzylic carbocation. That benzylic carbocation has been stabilized, and it's been slightly more stabilized because of the delocalization that happens in the benzene ring. So bromine will eventually go on that particular carbon. And it actually goes on it so well that this happens 100% of the time, folks, over the run-of-the-mill secondary on the other side. That's how selective these reactions will become based on delocalization. Based on delocalization alone. So there was a little bit of rehash about alkene reactions, adding HBr to an alkene, but now being able to talk about benzylic carbocations and the role delocalization plays, because back then we had no clue about delocalization or about the benzene structure. We had no clue that that even existed. And now we can bring that in and talk about it all over again. But we're not quite done. Let's do another example. So here's another example that we can look at, folks. Here is a diene. The question, is this a conjugated diene or is this an oscillated diene? Well, let's use our definitions. Let's use our new term. Let's use our vocabulary that we've learned. I've got a double bond to a single, to a single, to a single, to a double. There is no way this is conjugated. This is an oscillated diene. Now, I'm only doing that just to review some definitions and some terminology. That's the only reason that I'm doing it. So with this particular molecule, we are reacting this diene with HBr. Okay, not a problem, right? I have a double bond, and I'm just going to redraw the starting reagent, CH2, CH2, CH, double bond, CH2. And I'm going to look at these two different double bonds. Is there a difference between the two? No, there's no difference. It's the same double bond on both sides of the molecule. So, the double bond is going to break. There we go. I know you've missed that noise. And here's the side of attachments that open up. Hydrogen plays with other hydrogen, folks. So where's it going to go? I hope that you're going to tell me to the left-hand side because that's where those other hydrogens are. So there's my CH3 group, and there's the carbocation that forms. Now let's pause for a minute. Because here we formed a carbocation, and I have a double bond in the molecule as well. Up here at the top, this was an oscillated diene. So this double bond was fully separated from this double bond, so no delocalization happened at this particular level. Well, we have just cracked a double bond, and we have just started to add on reagent, and we have formed a carbocation. We want to double check ourselves. We want to make sure that delocalization cannot play a role here. If it does, then we have to consider that when we start looking at products that are formed from this reaction. So this positive charge and this double bond could be attracted to each other, and delocalization could form. Will it? And you better tell me no. Because this double bond, there's the sp2 carbon. The next door neighbor, whoop, right there, is a regular carbon, all single bonds, no positive charge, no double bond, no nothing. It's just a regular run-of-the-mill carbon. So delocalization is still not going to play a role here. And that's good news. I don't have to worry about all of that crap, right? All right, so where is that bromine going to go? Well, that bromine's going to go where that carbocation is at. That carbocation right now is a secondary carbocation. If it moved right-handed, it's still going to be a secondary carbocation, so carbocations are not going to shift either. So bromine is going to go there. All right? If you want to review some mechanisms, I can give you that mechanism review. We always started the curvy arrow at the negative site, which would be at the double bond, and I'm going to draw it to the positive piece, which is that hydrogen. Remember, HBr is polar, and that makes hydrogen slightly positive. Well, the electrons between the H and the Br will go over to bromine because bromine is electronegative and it was pulling them away from hydrogen anyway. So, folks, there's the mechanism of this reaction. Nothing has really changed, right? I mean, I'm looking at this and it looks like I could cut this problem out and slice it into the lecture videos that we did with alkene reactions. And you would be okay with this. The issue that some of you might have, though, is you might look at this and say, well, what about this double bond? What about that one? Okay, well, that one was kind of identical to the other one, right? I mean, it's a very symmetrical molecule. There's no differences in the positions of the double bonds because of that. If I named it, I would get the name no matter what, the same name. So this is a very symmetrical molecule. But how do I know that it didn't break both? Well, one of the ways that I know HBr was written, and that was the only thing that was written. If they wrote the word excess, then what they would want me to do is they would want me to look at this double bond and break that one as well and do the same thing. Hey, we get a side of attachment here, we get a side of attachment there, the hydrogen goes on and plays with the most hydrogens, and the bromine is going to go on in that location. They would say excess here, or they would say 2 moles, just to let you know, because there's 2 double bonds. So nothing special, nothing fancy has happened here in this particular type of reaction, all right? The only difference that we're playing with is this idea of just one HBr getting added or the idea of extra HBr getting added. But even that's not really a new concept because we saw them do this with our carbon triple bonds. We took a triple bond, we broke it to a double if there was 1 mole sometimes, right? And then if there was extra or excess or 2 moles of it, we doubled up. Then that double bond would then break and it would go to a single bond. We would do 2 steppers in those reactions. Same kind of concept here, except we've just 2 double bonds within the molecule that both can react just like the other one can, right? So this is an example of an isolated diene. There's no difference in what we've been doing, nothing at all. Just the concept of how much reagent do we bring into the picture. That's it. That's no more. All right, so let's do another example. Let's take CH2 double bond, CH, CH2, CH2, carbon with a methyl that points up, and then a double bond CH2. And let's add just 1 mole of hydrochloric acid. That's all that we're going to do. We're not going to do excess with this one. Why? You're getting ready to find out. All right, so this one is also an isolated diene. So I'm just going to write that up here to the side. Again, just a review, because this is double, single, 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 double. Okay, so this is not the typical double, single, double setup for me. That's conjugated. This is isolated. All right, so no big deal. But it's my job to figure out, if I'm going to react 1 mole of hydrochloric to this, where does it go? Does it go to the left-handed double bond or does it go to the right-handed double bond? Right? Which one? Well, keep in mind, if a molecule is going to get disturbed, if a molecule is going to get attacked, and a double bond is going to get destroyed, then it's going to make sure that it's okay with that rearrangement. meaning it's going to break in such a manner that it frees up the most stable carbocation. That's what goes on. So if the double bond to the left and two sites of attachment open up, hydrogen plays with other hydrogens, right? So in this scenario, the hydrogen would go here and a carbocation would form there. What type of carbocation is that? Well, you would look at this and you would go, hey, that carbon's one to the left and it's one to the right. So this is going to be a secondary carbocation, and it's not going to shift because if it does go right-handed, it's still a secondary. So it's going to pretty much stay where it's at. Okay, that's fine. All of that was review. None of that was new. It might have seemed new, depending on how much you paid attention to me, but none of that was really new. Well, if the double bond over here to the right-hand side, we get two sides of attachment open up here and here. Hydrogen plays with other hydrogens, so hydrogen will be forced to go to the right-hand side, and then a carbocation would form here. What type of carbocation is that one? Well, I would look here to the left, and I would look up, and I would look to the right, and I've got three groups on that. So, folks, that is a tertiary carbocation. Out of the two, which is the most stable? I hope you're going to tell me tertiary. It's something that we've only talked about all semester long. So that means out of these two choices, I have a diene. It's an oscillated diene, but that double bond to the left-hand side is not going to get touched. And the reason is because this is more prone to attack, because the molecule feels more comfortable saying, hey, hydrogen, you go on there, you play Makovnikov for me, and this carbocation would form at that spot, and that is a tertiary carbocation. And I'm okay with that, because if one's going to form, I want it to be formed on the most stable carbon, and that's where the molecule decides to go first. So if that's where that carbocation forms, there's no need for it to shift. That is where my chlorine is going to go. So this would be 1 mole. That's the product of 1 mole. What if we did 2 moles of it, though? What if this said excess? Or what if this said 2 moles? We have 2 double bonds here. We have a diene. Now, delocalization's not playing a role yet. This is just a rehash. It's a recap. That's all I'm doing. I'm preempting you in going into that field of delocalization with double bonds. But right now, we're keeping it simple. We're just doing a review. If 1 mole happens, there's my product. If 2 moles happen, then folks, that does destroy that second double bond. Hydrogen plays with other hydrogens in that scenario as well, and a chlorine does go on to that position as well. So it really depends on how much of the reagent, yet again, that they tell me to use when I see a molecule like this that has multiple double bonds. But once again, delocalization never showed up. Nothing. But it's getting ready to. So in the next video, we're going to do some of these examples. We're going to rehash these reactions over again, but we're going to choose molecules that delocalization could happen. How does that change your product? Does it change it at all? It's still 2 double bonds, isn't it? Well, we'll see. Go freshen up, go get a snack, come back, and I'll be waiting. Just bring me something back when you come.